Our paper is tailoring dual canal anchorable organic sensitizer with indolo 2 and 3p connexolin moiety correlation between the structure and the DSSC performance, presented by Muhammad Ramadan Abdullah and supervised by Dr. Ahmed Al-Shafi'i. Dye-sensitized solar cell DSSC was first designed by O'Regan and Gritzel in 1991, so we usually called it as Gritzel cell. Its advantage is the low production cost, multicolor design, transparency, flexibility in design, superior performance in diffuse light, and molecular design opportunity. Component of the dye-sensitized solar cell: the TCO substrate, semiconductors, dye-sensitizer, electrolyte, and counter electrode. In this paper, they are studying the relationship between the number of anchoring group and the corresponding photophysical, electrochemical, and photovoltaic properties. Two dual channel anchorable sensitizer were designed by converting the DDA by A configuration into a new DDA by A per 2 framework. The significant group of the FS13 and FS14 is the indolo 2 and 3p connexolin, which show high coplanarity with fused donor and acceptor, triphenylamine or carbazole as an additional donor, phenyl ring as the bi-conjugation bridge, cyanoacetic acid as an anchoring group, the hydrophobic carbon chain such as ethyl on the N terminal of the IQ segments for both dyes were employed to evade pi staking and to conduct the anti-aggregation. This slide illustrates the photophysical properties of FS13, FS14, and FS8 by drawing the UV visible absorption curve, which is for our 3 compound, which measured in the DMF. We found that the redshifted light absorption and the higher molar extension coefficient leads to better light harvesting ability. The electrochemical properties. From the figure we can see the band gap for the FS13, FS14 and FS8 are almost identical, equals 2.55 electron volt, which assigned to the IQ COM4 with the coplanar donor acceptor system. And also we can see that ESOP is above the CP edge of the titanium oxide, and this leads to an efficient electron injection, while the GSOP is below the redox potential, which leads to efficient dye regeneration. The relation between our course and the paper is studying the dye absorption on the working electrode, which follows the Langmuir isotherm, as it is due to the strong chiliation of the dye sensitizer with the titanium oxide, the limited binding sites on the titanium oxide surface. By application of the Langmuir isotherm, we can find that the KL equals C infinity titanium oxide divided by CS infinity multiplied by S titanium oxide minus C infinity of titanium oxide. This leads to the concentration of infinity of titanium oxide equals S titanium oxide divided by 1 over KL CS infinity plus 1. And as the limited of the concentration infinity of titanium oxide in compared with the dye size of titanium oxide, the relation becomes C infinity titanium oxide divided by CS infinity equals KL S titanium oxide. By drawing the relation between C infinity titanium oxide versus a CS infinity, we can find the initial slope, which is equals to KL S titanium oxide. The sensitization studies. At first, we will study the photocurrent photovoltage GV characterization of the DSSC sensitized with the FS13, FS14, and FS8. As we illustrated here, the GSC decreases with the order of FS8 more than FS14 more than FS13, and also the efficiency decreases in the order of FS8, FS14, and FS13. This means that the FS8 has the highest GSC and the highest efficiency. This is because its highest molar extension coefficient and it has best coplanar conjunction geometry, and this is resulting on the outstanding light harvesting ability. In this slide, we illustrate the photocurrent action spectra IBCE of the DSSC sensitized with FS13, FS14, and FS8. And we found that the quantum efficiency decreases into the sequence of FS8 more than FS14 more than FS13, which is according to the values of the GSC derived from the photovoltaic. So from that we can say that the higher molar extension coefficient had a higher harvest ability, had high GSC, had the better IBCE. This slide shows the electrochemical impedance spectroscopy EIS. And from the NICOS plot, we found that the electron recombination resistance decreases in the order of FS14, FS13, FS8. And from the boot plot, we found that the TCB equals 1 over 2 pi F. This slide illustrates the photocurrent action spectra IBCE of the DSSC sensitized with Hg2 alone and co-sensitized with FS13, FS14, and FS8. The order of the IBCE plots is in good agreement with their GSC value, and it takes the decrease sequence as the Hg2 plus FS8 is more than the Hg2 alone, and is more than the Hg2 plus FS14 is more than the Hg2 plus FS13. Finally, the electrochemical impedance spectroscopy EIS, NICOS, and boot plots for the DSSC sensitized with Hg2 alone and co-sensitized with FS13, FS14, and FS8. We found that the light time in CPH of titanium oxide of the DSSC was received from the boot plots and arranged in the order of Hg2 plus FS14 is more than Hg2 plus FS13, approximately equals to Hg2 plus FS8, which is more than the Hg2 itself. In conclusion of this paper, the two new dual canal dye anchoring organic dye FS13 and FS14 has been successfully tolerated and sensitized with the DDA by A pair 2 building configuration. The dual anchoring sensitizer presents less photovoltaic performance comparing to the mono anchoring dye FS8. However, the dual anchoring dye gave more positive co-sensitization effect by improving the Hg2 based device efficiency around 9% compared to 6% increase by the mono anchoring one. According to the examination of the co-sensitization effect, FS14 presents the best co-sensitization effect by improving the efficiency by 9.2% from 7.5 to 8.67%.
The paper I have selected is titled as Metal-Free Organic Dyes for Dye-Sensitized Solar Cells from Structure Property Relationship to Design Rules. Why the metal-free organic dyes for dye-sensitized solar cell is important? The answer is metal-containing inorganic dyes for dye-sensitized solar cell are very expensive, so scientists are looking for cheaper option. That is why metal-free organic dyes for dye-sensitized solar cells are very important. The article covered following topics. Firstly, design principle of dye-sensitized solar cells. Secondly, effect of electrolytes on power conversion efficiency. Thirdly, co-sensitization to increase the absorption spectrum by the combination of different dyes. And finally, organic p-type dyes for dye-sensitized solar cell with photocathodes. Dyes used in dye-sensitized solar cell can be classified into two categories. Firstly, functional ruthenium-based polypyridyl complex dye, and secondly, metal-free organic donor acceptor dyes. The basic building blocks of organic metal-free dye in dye-sensitized solar cell contains donor, pi bridge group, and acceptor. The pi bridge group is actually alternative carbon-carbon single and double bond. The acceptor group is connected with titanium oxide membrane that is coated over the photoanode. The basic components of dye-sensitized solar cells are photoanode, porous titanium oxide film over photoanode, sensitizer dye, electrolyte or whole transporting material, and counter electrode. When light incidents on photoanode, titanium oxide collects electron from sensitizer dye, then sends that electron to anode, then to counter electrode for electricity generation. Now I will talk about neutral organic dyes as sensitizers in dye-sensitized solar cells with liquid electrolytes. Neutral organic dye has high polarizability. It has tunable spectroscopic and electrochemical properties, and the core building block for this dye is on the right side. Here you can see donor, oligoin, and acceptor. Oligoin is pi conjugated bridge. The donor group is basically based on dialkyl aminophenyl, and the acceptor group is based on cyanoacrylic. We will see the figure of neutral organic dyes in the next picture. So here you see we have the donor group that is dialkyl aminophenyl, then we have pi conjugated bridge, and then we have cyanoacrylic. If we change the methyl group in donor with ethyl group, then we can see the change in short circuit current. It becomes 12.9 to 16.4. Then we can also see the change in power conversion efficiency from 6.8 to 6.6. That is how, if we use different combination of donor, acceptor, and oligoin chain, then we will have different power conversion efficiency. The next class of dye is ionic organic dye as sensitizer with liquid electrolytes. These kind of dyes are basically based on hemicyanin, merocyanin, scorillium, and cyanin based dyes. It has tunable absorption range from red to near infrared region, and it shows aggregation or self-association property which causes moderate power conversion efficiency. To improve the power conversion efficiency, we have to prevent self-aggregation or association. For this reason, if titanium oxide coated photoanode is treated with hydrochloric acid, it creates more active sites, which later increases dye migration at titanium oxide nanoparticle pore and prevents self-aggregation of dyes and increases power conversion efficiency. In the example, we see the donor is based on dialkyl aminophenyl, and oligoin is pi conjugated bridge, and acceptor is naphthothioleum. In the figure, you see there is negative ion and positive ion, and in 6T we see extra hydroxyl group. This extra hydroxyl group creates hydrogen bond with titanium oxide nanoparticle layer. That is why it has higher power conversion efficiency, which is 6.3%. Dye-sensitive solar cells with ionic liquid electrolytes. It has several advantages, like it has reduced volatility, high thermal stability, higher ionic conductivity, and long-term stability. The problem with ionic liquid electrolyte based dye-sensitized solar cell is higher viscosity than conventional liquid electrolytes. That's why it has slow charge transportation. Dye-sensitive solar cell with solid electrolytes. The advantages of solid electrolytes are no solvent evaporation, no leakage like liquid electrolytes, and good for textile based electronics. The disadvantages are inferior pore filling of porous titanium oxide by hole transporting material in this case, and it is not better than ionic liquid electrolytes. Now I will talk about co-sensitization effects in dye-sensitized solar cell. Most of the organic dye for dye-sensitive solar cell has narrow absorption spectrum. To increase the absorption spectrum within the visible range, dyes with complementary absorption property should be combined or mixed, and that is how we can increase the power conversion efficiency. Different research studies showed this approach to increase the absorption spectrum of the dye-synthesis solar cell. Previously, I have talked about N-type organic dyes for dye-synthesis solar cell. Now, I will talk about P-type organic dyes for dye-synthesis solar cells with photocathode. Here, you see the cathode is coated with nickel oxide coating instead of the photoanode. And the electron transfer from photocathode to the dye, and then it transferred to the counter electron, and that is how electrons run throughout the circuit. And the disadvantages of this kind of p-type inorganic dyes are it is not good as n-type photoanode, and it has lower power conversion efficiency. The future research can be done on p-type photocathode based dye-sensitive solar cell, co-sensitization, solid state hole transporting layer, ionic liquid hole transporting layer, effect of dye self aggregation, and controlling the dye migration on the titanium oxide porous film. Thank you. That is all about this paper.